Before starting today's lecture, I have a movie recommendation for you. If you have more time than usually because of the lockdown, it's suitable to this part of the course. I hope you're seeing, yes, you're seeing the title of the film. The title is A Beautiful Mind. It is about Nash. Nash is the scientist who discussed the topic of Nash equilibrium. So it is a nice movie. So I would recommend that you look at it. Today's lecture. Before starting with the flipped classroom, I would like to introduce the graphs. So graphs are powerful tools for modeling and analyzing networked systems. And there is a summary of 3 pages in my thesis. I would strongly recommend that you read it carefully because we will need the graph theory in this course intensively. What is a graph? I can go to the definition in my thesis. A graph is a pair that consists of a set of vertices and a set of edges. If more than one graph is used simultaneously, the sets of vertices and edges of a graph G are denoted by VG, EG, respectively. So this is what you see right here is an example of a graph consisting of the vertices A to E and the edges between them. It is a directed graph. There are also undirected graphs. So please read especially the definitions carefully. There is also an exercise which we are going to upload to Moodle. Please do it. So it is just to apply the definitions to this graph. Popular example of graphs are root networks and the routing in the root networks. So if you have a navigation system or if you just use some map materials on your smartphones, for example, Google Maps, then of course, first the navigation system should locate your position, and then you type a target position in the map, and you ask Google or the map service to compute a good route for you from the starting to the end position. And for this, maps are usually modeled as graphs. And there are, we can model them in different ways, but let's say vertices are the streets and the connection between the streets are the edges. And one of the famous algorithms in graph theory and in and it is very important for example a routing system, not just for root networks, also in the internet, to find the way for a data packet. If you, for example, ping a server on your PC, then there is a route the data packets follow. And the path between the source and the target, or between your position and your goal, is computed using a famous algorithm, or modifications of it, some heuristics. The algorithm is called Dijkstra algorithm. Dijkstra is a famous computer scientist from the Netherlands, and he found the optimal way to compute the path between arbitrary two nodes in a graph. So in the next slides, I illustrated the algorithm, but I'm going to skip it in this lecture, so you can read the algorithm or understand the algorithm in from a source you would like. Just type the name of the algorithm in Google, or you will find a lot of resources, for example, Wikipedia. And you can use the slides here to understand the algorithm. So it is very recommended to understand how graphs work and how we compute, how we use them to compute some measures we like. And the most famous one is the shortest path algorithm. And today is actually a flipped classroom, and the task was for Team D to prepare a summary of 15 minutes. By all of you, not just Team D, should have read pages 20 to 51 of my thesis. And I am now happy to see the summary of Team D. So I stopped my screen sharing. So I'm asking now Team D to share your screen and give the summary. Who is going to do it?
It's me and Clemens. So Marcus.
Can you all see the screen?
Clemens, yeah. Yeah, I see your screen.
Do you hear me? Hello?
Yes.
Yeah.
Okay.
Marcus and Clemens.
Yes.
Okay. Go ahead.
Good morning, everybody. My name is Marcus, and together with Clemens, we will be presenting Group D's flipped classroom topic, Network Model Predictive Control. Today, I will be presenting the basics of network control system. Afterwards, we will be presenting net MPC strategies, and at the end, we will give an overview of the advantages and drawbacks of each strategy. First, I will give an overview of the basics of network controlled system. An NCS contains active and passive agents. Active agents can be vehicles with network control, and passive ones are vehicles without them. An NCS is an integration of networks and actions, for example, in the fields of communication, computation, and control. It consists of multiple agents which communicate and interact over a time-variant network. The four characteristics of an NCS are: first, large scale. Multiple control loops allow for multiple control objectives to be achieved at the same time. Open. When the NCS is running, new agents can be added, information flow can be dynamically changed, or existing agents can be replaced. Time critical. The stability and the performance of an NCS is affected by a time delay in a control loop. And lastly, safety critical. It is hard to achieve a safety guarantee, and it causes severe consequences once it fails. NCS can be classified into different subsystems in a system level. There are heterogeneous dynamics and homogeneous dynamics. In a homogeneous dynamics NCS, each agent have the same dynamics. In a heterogeneous, at least two agents have different dynamics. Independently of these two categories, it can either be dynamically coupled or dynamically decoupled, which I will explain on the next slide. In a dynamically coupled NCS, the states or the inputs of an agent affect its own as well as other agents. On the contrary, the states and inputs of agents do not affect other agents in the case of dynamically decoupled NCS. In decoupled NCS, the agents can have coupling in the control level. In the formula on the right, you can see the mathematical differences between the two dynamically coupled and decoupled NCS. Finally, in NCS, coupling topologies can be differentiated into time variant and time invariant. The NCS has a time invariant topology if all of the following conditions are satisfied. The adjacency matrix is constant over time, all coupling objectives and constraints are active over time, and no agent leaves or enters the NCS at any time. An example for such an NCS is a vehicle platoon control or a wind farm control. An NCS has a time variant coupling topology if any of the above conditions are not satisfied. An example for such an NSC is a collision avoidance of network controlled vehicles. Each agent in NCS aims to track a reference trajectory with the smallest possible change in its inputs and while satisfying constraints on its states and inputs. Furthermore, they have to coordinate with other agents in the NCS. This problem is solved using inNetworked MPC. It can deal with the actions of other agents with respect to their future intention. In inNetMPC, an optimization problem is formulated and solved at each sample time to compute the optimal inputs. The interaction between agents is achieved through coupling, objective, or constraints. Networked MPC can be divided into further categories: centralized, distributed, and decentralized. Additionally, distributed can be further divided into cooperative and non-cooperative. In the following slides, Clemens will explain all these strategies.
Yes, thank you, Marcus. I will start with centralized if PowerPoint will work. Okay, so I will start with the centralized MPC. I hope you all can hear me. I will assume so. In the centralized MPC, all agents are connected to the center, and all agents communicate their current or estimated states, their predicted reference trajectories, and their model parameters to the center. The center calculates centralized optimization problems and communicates the optimized inputs to the agents back. The optimization problem, we have an example formula on the bottom, and I want to go through it step by step to show you what each part does. So since it does this optimization problem for all agents, we sum up the cost for all agents. And each agent occurs a cost that has three parts. The first part is the deviation from the reference. The second part is the cost due to changes in the input. And the last part are the coupling between the agents. And we have to be careful here because we only ever want to include a coupling once. So we have to be careful not to include couplings more than one time. These are the three costs that occur in each agent, and the whole cost is accumulated and minimized. There are some advantages and disadvantages. The advantages is that all agents communicate to the center, so the center has all information. There's only a single optimization problem solved by the center, and if a solution exists, the CMPC can find it. there are also some pretty big disadvantages. It requires a pretty complex communication network since all agents are connected to a single node. It occurs a high computational cost since the problem is pretty big and has to be solved on a single controller. There's only a single point of failure, so it induces a big safety hazard in case of failure, since only the center can compute the control actions for all agents. And if the center fails, all agents are pretty much, they cannot control themselves anymore and hopefully find a safe state. If the computational time is too high, it affects the whole NCS performance because all agents are affected by a single node that takes too long. These disadvantages are pretty big, and where can we actually use such a network? And it can be used in small time invariant systems where maybe the real-time requirements are not that high and there are not many agents, and the problem is that's not so complex, where it can be solved on a single node. It can be used in multi-level control strategies in high-level controller, or it can be used as a net MPC, as a reference for net MPCs, because the performance of network control systems are directly coupled to the performance to the solutions of the centralized MPCs. We can see this if we look at the criteria for the performance of NCS. The first criteria is the stability that has nothing to do with a CMPC, but NCS is stable if all agents are stable. The feasibility of a solution can be is two-part. The solution is agent feasible if each agent has a feasible solution, but the solution is NCS feasible if it's feasible corresponding to the CMPC. The optimality of the solution follows the same scheme. We can have agent optimal solution, and the solution can be NCS optimal if it's optimal corresponding to the CMPC. To find the quality of the solution of an NCS, we directly compare it to the solution of the CMPC, because we know the CMPC can find the optimal solution or the best solution, since it has all information and calculates the solution at the same time. So we see that the performance on the NCS, three criteria directly need the CMPC or an implementation of the CMPC to find to get the performance of the whole system. Now I want to continue with the decentralized and distributed MPC strategies. The decentralized is only not really used because it does not really have any, or has not much, is not much better than a non-network, because we'll see it later. The main idea from the decentralized MPC from the centralized is that each agent has its own controller, and each agent solves their own optimization problems. And as I said before, the agents do not communicate with each other, so it's not really that much network. So, and they only consider their own objective function and constraints. There's no coupling in the optimization problem. With the distributed MPC, we want to get a more centralized or more ideas from the centralized part. In the decentralized MPC, we still have that each agent has its own controller, but the agent communicates with its neighbors. And it takes other agents into consideration. And how much or what information from other agents are used in the optimization problem is dependent on which type of distributed MPC we look at. We have the cooperative distributed MPC and the non-cooperative distributed MPC. With the cooperative distributed MPC, the agent considers coupling edges with and between its neighbors. So if we look at the agent V1, we take into account the coupling edges E12, E14, and the coupling edge E24, because it is a connection between two neighbors that the agent knows. In cooperative distributed MPC, the agent predicts their own state and the states of their neighbors. And Yes. The non-cooperative distributed MPC considers only the edges that are directly connected to itself. So in the, again, example for agent V1, only E12 and E14 are considered. The agent solves only their own optimization problem, not the optimization problem of its neighbors. And agents send their predictions states to each other and use them in the optimization problem. The prediction consistency is not satisfied unless the NCS is fully connected. Now I want to compare the equations to show you again what the real differences between both approaches are. We see that both approaches compute their own cost due to deviations from the reference and due to changes in the input. But the cooperative DMPC also computes these costs for its neighbors. Both again use the couplings that are directly connected to itself, but the cooperative DMPC also takes it into account the couplings between its neighbors. Now we come to the end. We have a very nice comparison slide for all types of networked MPC types, and again, comparison and what is good and what is not so good for each. Most of this was already said. The centralized has a central controller, while the others have a controller for each agent. In the centralized, there's only a single optimization problem computed for all agents at the center, while in the others, each agent solves its own optimization problem, and sometimes, like in the cooperative distributed MPC, also solves an optimization problem for its neighbors as well. So sometimes the same things are calculated multiple times in the same network. In the what type of informations are used in the centralized MPCs, the controller takes the objective and constraints from all agents into considerations. In the others, in the decentralized, no communication with other agents, so the information cannot be taken into consideration. With the cooperative and non-cooperative, as we saw in the equations, they use different, the cooperative uses information between neighboring, between neighboring and the neighbors, and the non-cooperative doesn't take into account the constraints between neighbors. Yes. We want to thank you for listening to this short presentation, and we're more than happy to take any questions you have.
Thank you very much. Very nice presentation. Yeah, before opening the Q&A session, I would like you now to evaluate this course. You should have received an email, I think on Tuesday, right, Patrick?
Yeah, I think so, yeah.
Yeah, and there is a link inside the email. So, yeah, please do it. I cannot help you evaluating this course, but I would be very happy, really very happy getting feedback from you. So this year's course is more or less the result of the evaluation of last year, and you you can influence this course for next year if you would evaluate it. Yeah, in general, it is important for us to, of course, to get feedback from you. Of course, we are happy to get positive feedback, but we are also happy to read your your criticism. So I would say, yeah, you have some minutes to evaluate this course, and we will continue after that with the Q&A session. I hope you have done it. Yeah, I will get the results of your evaluation after the end of the evaluation period, and I will discuss the evaluation results with you. It's going to be in 2 weeks. So in 2 weeks, we are going to discuss your feedback. And now I would ask Marcus and Clemens to share your presentation again. And yeah, the floor is open for questions. So maybe I start with a simple question. What are your study programs, Marcus and Clemens?
I study computer science.
I'm at the Computation Engineering Science study program.
Okay, CS. Okay. Yes. Yeah. Good combination also in the lab.
Yeah, no, Marcus and I am not in the same team, but
okay. The
so
same
we all prepared the presentation together, but only two presented because it was easier to coordinate the presentation with two people.
Okay. Okay. So this is a flipped classroom. It lives from the feedback, from the discussions, from the questions. It should not in all cases be a question. It could be also a comment. What you would like to tell. I can't believe that you don't have questions. So you will be able to answer every question on this topic if you don't have questions. Maybe I start with a question about decentralized control. Clemens, you said decentralized control isn't necessary. If it is not necessary, why we are studying it?
I think I wanted to express that decentralized control is, from my understanding, not really a network control strategy, because there's no communication, and so it would, from my understanding, it would basically be the same if we were in a non-networked control strategy, if all controllers were, or all agents were non-networked. So it is what I wanted to express. It's not really a part of the network control system part, but it's all levels of networked, and if no network is also a level of network. But
I expected this answer. It is actually the modern answer, and yeah, of course you grow up in this century, but back in the days, 30 years ago, there were no, at least no good communications networks, and despite of that, yeah, it was necessary to implement non-centralized controllers. For example, in electric grids, they were also working before the communication, the information communication networks were established. And yeah, if we don't have information communication, we can get knowledge about the other agents from, for example, the estimation of their states. There is no direct information communication, but there are other ways to estimate states of other agents. For example, a typical example for this decentralized control, without information communication is an electric grid. Of course, we can here start discussing about information, definition of information, and if the grid is connected, right? And we can also say it is we exchange information, but it is not directly in the classical way we do it today, with really data buckets where we have really coded data.
So it's more communication over the medium it controls rather than a separate network for data flow.
Say it again.
So these for decentralized MPCs, they communicate more over the medium because they are influenced by other control decisions of other agents, but they do not communicate directly to these agents, but only can react to changes that they experience with their own measurements that are on the same medium, like the electric grid, or I don't know, cars that all have their own agent, but only can detect each other via other measurements, but exist on the same street.
Yeah, right. And an additional note on these terms of decentralized and distributed. These terms are not really unified in literature. It could be that you find decentralized control in literature, but they mean in our terms distributed control. So as always, to start a topic, you need definitions. And you can define how you would like to define terms, but your definitions should make sense. And I used here a source from a book from 2014 about the definitions of decentralized and distributed, but there are other research groups. They say, okay, they speak about decentralized control, but from our point of view, they mean distributed. Okay, no problem if they define it. We get it. Okay, they mean distributed in our case. Then we can continue thinking with them, and we can understand their research. So the same for cooperative and non-cooperative. The definitions here are from game theory. And it could be that other groups could speak about non-cooperative control as non-cooperative distributed as a decentralized control. Could be, but we have our clear definitions here. We say what is cooperative, what is non-cooperative, what is distributed, what is decentralized, and important in definitions is to be consistent in your work to define something and to stay to this definition, not to change your definition from day to day. Yeah, this was a general note.
Yeah, if there are no more questions, I would have a question. Because there was a value, I think it was had the name alpha. I didn't remember the correct name. Maybe it was the coupling coefficient. Yeah,
Yes.
exactly. On the left side, the alpha value, and I read that it's a value based on the matrix and or about the adjacence matrix, and represents the connection, the height, the level of connection of the matrix. But I didn't really find a lot in the internet about it. Could you maybe tell us a little bit more about this value, how it's computed, and yeah, what kind of values could it be? Is it a discrete value or a continuous one?
Does anyone from my group want to answer?
I could try to answer that. It's usually the number between 0 and 1, and the literature doesn't really mention how it is computed, but a lot of it is still open for the next research. But we need to multiply this value with the computation of this optimization for the neighboring agents, because for cooperative DMPC, we each agent only take account from the objective and constraints of their neighbors. That means they cannot really predict, they cannot really make a correct prediction of their neighbors. So it has to be kind of weighted if how correct the prediction for each one of their neighbor is. Yeah, so the value is between 0 and 1.
In the literature, it also said that it is calculated by the adjacency graph matrix for the network. So if we take agent 1 as our optimization, where our optimization problem lies, and we look at agent 2, we only know 2/3 of its coupling costs, because one coupling we do not have any information about. So we cannot be sure that our solution for its values are correct. So we have to make the influence, so it should not influence us that much as if we knew everything about the other agent. That was my understanding for this factor.
Okay, but does that mean that if the other agent has a lot of connection to agents we don't know, then the value is near to 0? Because it's hard to predict or no, to optimize his problem, because we do not know a lot of his neighbors. And if we know all his neighbors, or he has no neighbors except us, then the value would be near to 1.
That was my understanding. But maybe Bassam could also.
Yeah, thank you to Petk and Clemens. Your answers are very good, and also to Paul, this is a really, really very good question. So alpha is very important, very essential for cooperative control. And yeah, obviously it depends on the graph. And we said, okay, it depends on the adjacency matrix, on the Laplacian matrix, maybe on the degree matrix, on somehow on some measures of the graph. This is obvious. That it depends on the graph. What alpha says is how if we have two agents, to give an example just to understand more what is alpha here. If we have two agents, the two agents are two pedestrians heading to each other from the last lecture, and agent A considers its own objective and the objective of B, and B does the same, then we can get a solution, because then we have somehow centralized control. What alpha says here, how much seriously I take the other agent. So if two pedestrians are heading to each other, A takes its objective completely into consideration, but agent B not completely. And why we do that? Clemens, if you go to a graph, I don't know, alas, yeah, it's good. So what Clemens said, agent V1 has information about 2 and 4, but not about 3. But 2 and 4 have information about 3, so they consider 3. If I consider 2 and 4 completely, then I'm doing mistakes, because they consider also 3, and I don't have information about 3. So a possible solution here, or the general modeling of this problem, is to model it as this alpha. This alpha could be also time variant. This alpha is not just a value, could be different between the different agents. And actually it is a core part in cooperative control. Obviously, if we can determine good values for alpha, then we can apply cooperative control. But it's not easy to compute good values for alpha. So a PhD thesis is running now in my group, and a big part of the thesis is going to be how to get good values for alpha. But alpha here is the modeling, how we express the problem. Of course, in the thesis, the result is not going to be a magic number like alpha should be 0.5, for example, but it's going to compute, let's say, feasible cooperative control. Maybe before we continue, maybe it is worth here to speak more about the prediction consistency. Maybe you can, the group can give more information about the prediction consistency, maybe a definition and some details and some examples. It's really very important. It is the main problem in distributed control, and groups do research on how to get distributed control feasible, And actually, it is all about, if we consider networked MPC, it's all about getting feasible solutions, all about holding the prediction consistency property. So there is also other PhD thesis, that one of Patrick is also more or less about how we get consistent predictions. Yeah, if you have some comments, maybe can give a definition.
I can do that as well.
Yeah, please.
So what each agent does is to compute the solution for the optimization problem, and to do that, they need to have the prediction of the state of themselves and also of their neighbors. And at a random time point, the prediction that one agent has for the other specific agent has to be equal to the prediction that that specific agent has predicted for itself. And in the case of cooperative distributed MPC, each agent computes the prediction for themselves and also for their neighbors with the information they get from their neighbors. But at the same time, the neighbors also compute a prediction for themselves and for their neighbor as well. But each agent, one agent don't know everything about their neighbors. So the prediction that they compute for their neighbor will probably not be equal to the prediction that that neighbor predict for themselves. And that means the consistency, the prediction consistency is not satisfied. And for the case of non-cooperative distributed MPC, each agent does not compute the prediction for the neighbor. Instead, the neighbor would send the prediction that they compute for themselves to their neighbors. But due to the time delay in the communication, the prediction that one agent gets from their neighbor will not be up to date. So, and here, the prediction consistency is not satisfied as well. And yeah, I hope that answers the question.
Oh, thank you, Dirk. Maybe there are further questions.
Yeah, I have one more question about the equations. Because yeah, we sum up the error of our states to the reference, but we sum up only the first values until HP. And I want to ask why HP, why we use separate function for computing the error for HP. Is it because we want to wait the last time point a little bit more, or why do we do this? So, did you understand my question?
I understood your question, but I think Team D should first get the opportunity to answer the question.
My understanding was more or less this has to do with how the sums are. Also, for me, it doesn't really make sense as well to take it out of the sum and not to sum up to HP. I would maybe, for me, I used a similar strategy in one of my courses where we had the error function decreases their cost with advancing time step, because the prediction gets most probably less and less accurate for further advanced time steps. And we use something like that. And maybe it's something in this direction, or it was used simply to have a similar sum with deviation in input, and but I don't know.
Maybe further comments from other members of the group?
Hi, hello. Can you hear me?
Yeah.
Yeah. So, like, just to add something, like, I feel like they have been taken separately because, like, the terminal states, like, they have their own different constraints. So probably they didn't we didn't sum it up with the previous ones, like a time step before the terminal state. So probably that's the reason they summed it up like in a different equation.
Can you say it again? I didn't get the main point. Sorry.
I said like this equation denotes the terminal state of the agent, like the prediction horizon HP. And they have a different set of constraints for the agent, and the set of constraints for the agent in the first equation where it's HP -1, it's different. So that's why they took it as a separate sum. That's what I understood from the equation.
Okay. Maybe further comments from other people in general from the course, not necessarily from Group D. Okay, then it is my comment. Yeah, this has nothing to do with networked. It has something to do with MPC, just MPC, not with the network. So we discussed this one or this question, maybe not in much detail in the MPC course. So yeah, the way or the separating the last prediction point is to have different evaluation in general. So weighting is also an evaluation, to have different evaluation of the very last point in the prediction. And different, I mean, it should be higher weighted. So the weight on the last step in the prediction should be higher. And if you look also into the constraints, you see that there is also a different constraint on the very last prediction. This is equation 314, right? Yeah, it is equation 314. And why we do that? It is because of stability. So I can try to explain it in words, but there are mathematical theories behind this. if we have an MPC and weight the last step in the prediction horizon higher, and if we have more conservative constraint on the last step in the prediction, then the MPC is stable. But of course, the question is how to higher weight and how to constrain the last step. To compute these things, we need another optimization problem, and yeah, these are different computations. But from the point of view of practice, we can just say, okay, it is a parameter for engineers. So if you have to separate the weights of the predictions till HP -1, and for HP it should be different. And you have to, let's say, play with this parameter to get the MPC stable. And another parameter is the constraint on the very last step. So maybe you can give me the screen sharing, then I can try to draw an example. So again, my screen. So maybe I can draw it directly here. So let assume there is a vehicle actually driving in, or currently driving in this direction, and let's say, to have similar examples of this course, we have here a static obstacle, and the reference trajectory is, maybe I take a different color. The reference trajectory is the straight line. And let's say somewhere here is the target. So this vehicle is driving from west to east. There is an obstacle on the way. The reference trajectory is the the straight line. And maybe I take another color. Now in the prediction, let's assume we are predicting from the point where the vehicle is now to a point here behind the obstacle. And we are optimizing, and to have a collision-free trajectory, we have to avoid the obstacle, of course. And we have also limited steering possibilities, and we have some dynamics model of the vehicle. We have modeled the obstacle geometrically, and so on. So I'm skipping these points. So, and let's assume the MPC is trying to find a solution, and let's assume this is a solution. The MPC starts to steer the vehicle. This is the solution in the prediction, right? So this is the optimal solution, or the solution of the MPC. So it is not the optimal solution, it is a possible solution. So, but it depends on the modeling. So we get somehow a trajectory, it deviates from the reference trajectory. And if the MPC is, or in general, if the control here is unstable, then we will not get back to the reference trajectory. Somehow, we will get something like this trajectory, right? This is an unstable solution. We avoided the obstacle, but we are far away from the reference trajectory.
Sorry, can I ask a question about this?
Yeah.
Yeah. So, okay, I can't imagine how we can get so far away from the reference trajectory, because so in my imagination now, the error between our predicted path and the reference is so high that it doesn't matter. So the only thing I could imagine is, for example, that we now have to steer in the other way very hard, and the steering error is higher than the reference trajectory error. So is this a case that could cause this?
Yeah, this is an example of unstable. This is not a good solution. This is unstable.
Yeah, of course. But yeah. So what causes this instability?
The modeling of the MPC. Your modeling is bad.
Okay, so for example, the weighting of different errors is not very well.
Not necessarily the weighting of the errors. In general, the change of the steering angle. In general, the modeling, all parameters, all modeling things in the MPC, they could lead to unstable solution. Yeah.
Okay.
Okay, this is unstable, and unstable is not a solution. It is something what we don't want to have in control in general. Yeah. And what could happen now if we continue? If we want to get back to the reference trajectory, then we would have here high steering angle. Yeah, it is just an example. Yeah. Let's assume we continue in. Maybe I take another color. Let's take green. So in let's assume we continue in our we drive on this trajectory, and we continue in our predictions, and from step to step we will try to get back to the reference trajectory, but we will try to get maybe very hard to the reference trajectory, because we want to get back to the reference trajectory. We steer a lot, but this steering leads that we hit the reference trajectory, but we miss it again. So we try again to get back, and we miss it again, and yeah, this is at least an oscillation, but it could be unstable. And what can we do to avoid this instability? Let's take another color. We can say, okay, MPC, you can do whatever you want in the prediction horizon to be optimal, to fulfill the constraints and so on. But please, the last point in the prediction should have a higher weight. The importance of the last point in the prediction is higher than the other points. And what we do with this with this weighting, we try to push as possible this point towards the reference trajectory. And doing so, we get theoretically a stable MPC. But of course, we have to find the right weight. So it is, again, I say it in general words, do whatever you want. In the last step in the horizon, you should be at the reference as possible. Is it more clear, Paul?
Oh yeah, it is.
Okay.
So the reason of HP, it's not. I think for me it's clear.
Yeah. If you want to dive more deep into it and to get the mathematical background of it, so I can email you the sources you could study. So it is out of the scope of this course, and it is a lot of stability theory. So it is out of the scope of this course, as I said. So in the remaining time, I would like to go through my my summary of this part of the course. If you have questions, just stop me. So yeah, most of the slides I'm going to show you have been shown by Clemens and Marcus. So I will go just fast through it, and if something is new, I will stop at it. So these are some examples of NCS. Here we see the definitions of passive and active agents, a classification of agents, communications, and yeah, time invariant and time variant network. Just some terms, and here's the whole view of the classification of NCS on the system level, control level, and algorithm level. Here we see the definition of a control strategy. It is the combination of the control method and the algorithm applied to it, and how we select control strategies. So some measures to select control strategies. Definition of computation time. This is very important. So the computation time is the time from the measurement to the application of the solution, and it includes also communications. So here we see again the details of the system level, the control level, and the algorithm level. And yeah, the focus in this course, and our focus in our group also, is on reducing the computation time and communications while enhancing the feasibility and the quality. So this slide is very important. I would strongly suggest that you study it in much detail. Yeah, it could be part of the oral exam. So what we see here is the difference between MPC and networked MPC, and yeah, the marked parts are the parts coming to the networked MPC. They were very nicely shown by Clemens. I'm not going to repeat it. So again, centralized, MPC and the definitions, the terms in for NCS and net MPC were also very nice, given by the summary of the group. Here we have cooperative is also very nice, and here is a definition of the prediction consistency, and I would like to go through this definition. It's really very important. So prediction consistency means that predictions J, T plus K, K1 to HP. So the predictions, just a second, okay, used or computed in the optimization problem of an agent VI. So we have an agent VI, and it computes the prediction of an agent's VJ. Yeah. At a time instance T for an agent VJ coincide with the predictions computed by agent VJ itself at the same time instant T. So with other words, what I think about you, you think about yourself. And what you think about me, what you think about me, I think about myself, if we have two agents. And in a network, it's always the question, what an agent predicts about another agent if it coincides with the prediction of the other agent of itself. So this is really main criteria for feasibility and stability of network control. We cannot apply network control without the satisfaction of the prediction consistency. So why cooperative control doesn't satisfy this property was very nice, described by the group, and we have here the non-cooperative distributed MPC, and again the definition is given here, and non-cooperative DMPC doesn't satisfy also the prediction consistency property, and this you have experienced in the last lecture in our pedestrian examples. Well, this is the same example we did in the last lecture, but for vehicles. We have two vehicles, 1 and 2, are driving from west to east and from east to west. They are symmetrically located with respect to the y-axis. They have the same velocity, and we assume a time delay of 1 time step. So what you saw in or experienced in the last lecture, the same is happening here. They move to the same direction. They go both back again to the reference, try again to avoid, and so on until the collision cannot be avoided anymore. Again here, a slide to recap the pedestrians walking example. And here we see an analysis why it is happening. If we take a deeper look on the graph of the non-cooperative DMPC, it is directed and it contains cycles. So the coupling graph contains cycles. The two agents are considering each other. So I consider you, you consider me, and this means a cycle in the graph. Yeah, cycles lead to the loss of the prediction consistency property, which is obviously, if you remember the example, I consider you, you consider me, and we don't find a solution. So there are two different solutions to this problem. One solution is solve in sequence and iterate to get a better solution. This is in general the solution in the literature. We say, okay, the problem you experienced in the pedestrians walking, if we say, okay, pedestrian A plan and B just stop, don't do anything, and then we tell B, okay, now you can plan, and A, you take a break, yeah, from planning, and so on. Then we solve the problems in sequence, and then we will get a feasible solution. And what we can do to get closer to the optimal solution is to iterate, to say, okay, A, compute, then B, compute, then again A, then again B, and so on. So you, it is like a negotiation or debating to get to a common solution. And other solution, which is proposed in my thesis, and where we take a deeper look in the structure of the graph, and where we can use the graph structure to somehow order the computations, and also to say, okay, I don't necessarily need iterations, or I don't want to have iterations because they cost time. So they are time costly. And just to compute in sequence, if we have two agents, you could say, okay, it is fine, two agents can compute after each other. Yeah, it's fine. But what if we have n agents, and n is a big number? Then it will take long time, very long time to get to a solution. And what we say, okay, we don't need to always compute in sequence. If we take a deeper look into the graph structure, then we can save some computation time. And if we look at the next slide, I think this is going to be the material of next lecture. It is pages 51 to 77 of my thesis, and team E is going to prepare the summary. So it is a flipped classroom, not just only team E, but all of you should read this part of the thesis. If you read it, you can make some questions or comments, and we can discuss it here. And this is the really the advantage of the flipped classroom, that you study the materials at home, and we discuss them here in the lecture to deepen your understanding of the materials. And you are advanced in study, you are not more undergraduate student, you are master's students, and in maybe 1 to 2 years, you are going to work somewhere, and you have to work independently, and you have to to be able to study your to study new materials by yourself and understand them by yourself, and you have also to be able to discuss what you developed, what you researched, whatever where you work. You have to be able to discuss these topics with your teams. So works nowadays are happening in teams. So we are trying to improve the teamwork in this course. So I think looking at the time, we still have 3 minutes or up to 3 minutes. If you have further questions, so please go ahead. There is something in the chat. Team E, I only know group. I didn't get the point. Okay, group. Yeah, right. Yeah, you're totally right. Not team. It should be group. Yeah, I will correct this. Thank you very much. You are very precise. So I'm always happy to get precise feedback. So I will correct this. Maybe it was also wrong on the other slides to flipped classroom. So I will go through it and correct it. So do you have other questions or comments? So if not, I am excited to get your summary in the next lecture. And with this, we close this lecture and see you next week. Bye-bye.